Welcome to a tutorial on quasi-linear equations. In this we are going to solve some Cauchy problems for quasi-linear equations, and we also explain through examples the local nature of solutions to Cauchy problem. Recall that the existence and uniqueness theorem gave us existence of a solution only nearby any fixed point on the datum curve. So, is that all that can be expected, or can we get a solution whose integral surface consists of the entire datum curve or defined on entire domain omega 2? These are the questions we are going to discuss under this heading on the local nature of solutions to Cauchy problem. So, let us start some problems examples. This is the simplest example that we considered in the beginning. Ux equal to 0 and data is u0 y equal to sin y. So, how do we solve this? We need to first parameterize the given Cauchy data, x equal to 0, y equal to s, z equal to sin s, and y in R, therefore s in R. So, this is our datum curve. Then we need to look at the characteristic system of ODE for the given equation. Recall dx by dt equal to a. In this example AUX, that is a is 1, b and c are 0. So, dy by dt equal to b, which is 0, dz by dt equal to c, which is 0. So, this is the characteristic system of ODE associated to this equation. Now, we need to solve these ODEs, system of ODEs. So, with the initial condition, so that at t equal to 0 you are at a point on gamma. So, x of 0 when time is 0 equal to 0, y of 0 is s, z of 0 equal to sin s, because 0 comma s comma sin x is an arbitrary point on gamma, the datum curve. Solution is very simple to obtain. So, we get x equal to capital X of T s equal to t, y equal to capital Y of T s equal to s, and z equal to capital Z of T s equal to sin s. That is very easy to see, because see here dx by dt equal to 1, therefore x has to be t plus constant. At t equal to 0 x must be 0, therefore this is the x equal to t. Here dy by dt is 0, that means y is constant. At t equal to 0 it must be s, therefore y equal to s. dz by dt equal to 0, that means z is constant with respect to t, but at t equal to 0 it should be sin s. That will give us the solutions. Okay. Now, we need to eliminate, or we need to solve for t and s in terms of x and y from the first two equations, which is obvious in this example. T is capital T of x y equal to x, s equal to capital X of y, capital S of x y equal to y. So, we have got this. Now, we need to substitute in this and we get the solution. So, u x y equal to sin y, which is defined for all x y in R2. This is a picture that we have already seen. The red is x axis, green is y axis, and this is z axis. And this one which is in magenta color is the initial data u0 y equal to sin y. So, 0 comma s comma sin s, as varies in R, you get this curve, and the integral surface is a blue color one. These are the characteristic curves. Here they are straight lines. We already saw that. Let us look at another example. This is also linear equation, ux plus uy plus u equal to 1, and the Cauchy data is of this nature. It is prescribed on some curve u of x comma x plus x square equal to sin x. So, as before you need to parameterize the Cauchy data. So, s x equal to s, y equal to s plus s square, and z equal to sin s, and for s positive. Done. And we need to write characteristic system of ODE. dx by dt equal to a. In this example a is 1, dy by dt is b, b is 1, dz by dt is c. Remember, c is anybody who is on the other side. So, it will be 1 minus z. You have to be careful there. Do not think it is 1, it is 1 minus z, because equation is of the form aux plus buy equal to c. So, dz by dt equal to c, therefore, it is 1 minus z. Now, we need to solve the system of characteristic ODE with the initial conditions which are given here, and we get solutions as this: x is t plus s, y is t plus s square, z equal to 1 minus e power minus t plus e power minus t into sin s, fine. Now we need to find t and s as functions of x and y using the first two equations, x equal to t plus s and y is equal to t plus s square. It is not clear to me how to get it, but let us ask whether it is possible to get at all. So therefore, yeah, here it looks like it is possible to get. So t plus s is actually x, therefore s square is equal to y minus x, therefore s equal to root y minus x, okay, because s is positive, that is why I am not taking minus. So root y minus x. So once you know s, t can be obtained from here x minus s, that is why x minus root y minus x, yeah, so it is possible to get. And then substitute for t and s in this formula for z, you will get a solution, it is a solution. And now question is, we have got the formula, ask what is the domain on which it is defined. First of all, you need that y minus x should be positive because there is square root, that is it, everything else is fine. So y minus x is positive, that is the restriction, which is y is bigger than x. So that means it defines a solution in this domain x y in R2 such that y is bigger than x. So this is the integral surface, it is in blue, datum curve is in green. So along this line y equal to x, the formula has a problem, right. So you will see that corresponding trouble here when y equal to x, on the line y equal to x. Okay, let us look at another example. In this example what is happening is ux plus 3y power 2 by 3 uy equal to 2. Now a is 1, b is 3y power 2 by 3. This is not a C1 function. Our theorem required C1 function, right? It is not C1 function. Let us see what happens. C of course is 2, constant, no problem. Cauchy data is u of x1 equal to 1 plus x. So first thing as always is to write gamma in the parametric form, which is this, and characteristic system of ODE is this. Now we need to solve this system of ODE with initial conditions. This solution is this, x equal to t plus s, y equal to t plus 1 whole cube, z equal to 2t plus s plus 1. Now from the first two equations we get t equal to y power 1 by 3 minus 1 and s equal to x plus 1 minus y power 1 by 3. Okay. In fact, for t you use this equation because it does not have s. So from here we get t, once you get t substitute here you get for s, that is why we got this. Now go back and substitute in this formula, x plus y power 1 by 3, and where is it defined? It is defined everywhere, but then everywhere in R2 because this is just cube root of y, right, cube root of any real number makes sense. But the problem here is that it is not differentiable at y equal to 0. So we have to choose either y positive or y negative. We have chosen y positive, and these are the views of the integral surface with the different orientations. Remember always the axis, red is x, green is y and the blue is z axis. So you see that some steeping is happening here around y equal to 0, it should happen, right, because y power 1 by 3 is there, it is not differentiable, so something it should be reflected in the picture. Okay. Let us look at another example. This is a very non-standard example. This was constructed with something else in mind, but it turned out to be, it is a very good example. It is a quasi-linear equation. So far we have considered only linear equation, but this is a quasi-linear equation, sin u ux plus uy equal to 0. Here a and b, a is sin u, if a is 0 b should be non-zero, but b is always 1. So it is a square plus b square is non-zero, fine. Cauchy data given is u of 0 y equal to y for all y in R. Let us solve. Parameterize the Cauchy data, 0 s s, s in R, characteristic system of ODE is this. Now because of the quasi-linear nature, equation for x actually involves z now, whereas y and z it does not involve any other variables. So from here you can see that along a characteristic curve z is constant because dz by dt is 0, and what is dy by dt equal to 1 means y equal to t plus constant, therefore because at t equal to 0 it should be s, y is t plus s. Z is constant and that constant has to be s. Therefore, you put that s here and integrate this. So, we get sin s into t, and at t equal to 0 it should be 0. So, this is the solution, y is t plus s, z is s. Now, using x and y equations, we have to get an expression for t and s, but you see I do not think it is possible because t sin s is there, this is t plus s. So, this is okay, nice, t plus s, but there is a sign here. So, we cannot express, I cannot express explicitly. Then I ask, is it possible for anybody to express at all, which means is the inverse function theorem applicable? We will check that. This was not the case so far. In all the earlier cases we could solve, maybe it is a bad function of x and y, it does not matter, but we could explicitly solve. Here explicitly we are not able to solve, fine. So, to know if a solution exists, we have to rely on the existence uniqueness theorem now, we have no choice. So, in this example we are not going to get explicit form of the solution because we are unable to invert, we are unable to write t and s as functions of x y. So, when you look at the whether it is possible at all, the J0s turns out to be sin s. Of course, sin s is 0 when whenever s is a multiple of pi, okay, all integral multiples of pi. Other than that it is always non-zero. So, if s is equal to k pi for some k integer, this Jacobian is 0. If it is not like k pi for some k, then it is always non-zero. These are all isolated points. Okay. So, Jacobian, if you remember, we have pointed out the ways of failure of transversality condition, and there we said it is a possibility that you have a sequence Sn along which j is 0, okay, but here and converging to some point, here it is not happening, these are all isolated points, okay, there is no convergent subsequence of these multiples of pi. Okay. Otherwise, Jacobian is non-zero. Therefore, local existence and uniqueness theorem is applicable whenever s is not a multiple of pi. So, in terms of y naught, it is y naught is not an integral multiple of pi, and we conclude that there exists an integral surface for the given PDE containing p naught and a piece of gamma. Of course, question remains, what happens when s is an integral multiple of pi? That is to be explored. So, now let us look at some examples which illustrate the local nature of solutions to the Cauchy problem. Before that, let us revise the notion of local solution. In initial value problems for ODEs, this is the equation we consider dy by dx equal to fxy and yx not equal to y naught. This is initial condition. So, both equation and initial condition together is called initial value problem, called IVP in short. Of course, we need to assume something on f. Let us assume that f is a continuous function. Now, a solution to the IVP which is defined on the interval I is called global solution. What is I? I is here. This ODE makes sense for x in I, and if you have a solution which is defined for every x in I, we call it global solution. Imagine it is not the case and solution is defined only on a subinterval of I, the proper subinterval of I, then that is called local solution. Now, recall that Pinot's theorem and Cauchy-Lipschitz-Picard theorem, whenever it is applicable, always guarantee the existence of a local solution to IVP. Okay, they do not talk about global existence. There are other theorems about global existence, and there is a full understanding of what happens if a local solution can be extended to make it a global solution. If you fail somewhere, what are the precise reasons why you cannot extend it to a global solution. So, that is very much understood for initial value problems for ODEs, but that is not the case in my opinion for partial differential equations. I have not come across such results. Okay, let us now define for partial differential equations. A solution to a Cauchy problem for a quasi-linear equation, it can be for any equation, first order PDE. Because we are in this first order PDE setup and this is a tutorial on quasi-linear equations, we can as well assume for quasi-linear equations, otherwise concepts are quite general. So, a solution to a Cauchy problem is said to be a global solution if this is where something comes with respect to datum curve. if the corresponding integral surface contains the entire datum curve. Okay. You have a solution, right, then look at the integral surface z equal to xy, entire gamma if it is on that, we say it is a global solution with respect to datum curve. Otherwise, the solution is called local solution with respect to datum curve. We have another related notion. A solution to a Cauchy problem is said to be a global solution with respect to domain, with respect to domain. If the solution is defined on the domain omega 2. What is omega 2? Omega 3 is the set on which the quasi-linear equation was defined, right, the coefficients a, b, c, they are defined on omega 3. Projection of omega 3 to xy plane is omega 2. So, you would expect that solution should be defined throughout omega 2. If it is so, we are happy and we will call it global solution with respect to domain. Otherwise, solution is called local solution with respect to domain. Recall the existence and uniqueness theorem proved in lectures 2.6 and 2.7. They guarantee, the theorem guarantees the existence of a local solution with respect to datum curve and with respect to domain, both. Now, since gamma 2 is a subset of omega 2, okay, if a solution to the Cauchy problem is global with respect to domain, that means it is defined throughout omega 2, it is also defined throughout gamma 2. Gamma 2 is a projection of gamma, so it should be global with respect to datum curve. Observe that if a solution to the Cauchy problem is local with respect to datum curve, then it is also local with respect to domain. Okay, now this is a remark applicable for semilinear equations. Recall that the base characteristic curves are defined as projection to omega 2 of the characteristic curves in omega 3 in the context of general quasi-linear equations. But in a semilinear equation, what happens is that base characteristic curves can be found out independent of the characteristic curves, because the equations governing the base characteristic curves, namely dx by dt equal to a and dy by dt equal to b, involve only x and y. A and b are functions of x, y only, it does not depend on z. Therefore, base characteristics can be found independent of characteristic curves. Now, we observed in step 2, namely in the proof of the existence uniqueness theorem, there we observed that the equation for z may not admit solutions for all t for which base characteristics are defined, simply because the dz by dt is a nonlinear equation. For a general semilinear equation, dz by dt is a nonlinear equation, and solutions to nonlinear equations, as we said, as a rule are only local solutions. So, it can even cut out some portion of this base characteristic curves. So, this might result in a situation where projection of a characteristic curve may not be the entire base characteristic curve that you already found otherwise. Let us assume all these curves are the longest possible things that we have found. We will see an example, it will be obvious. So, the next example exhibits this possibility. Ux plus uy equal to u square and Cauchy data is ux 0 equal to x. I think this is the simplest complicated semilinear equation, because u square is the first equation that we learn even in ODE, dy by dx equal to y square, that is the first nonlinear equation that we will come across in first order ODEs. So, let us parameterize the given Cauchy data, x equal to s, y equal to 0, z equal to s, s in R. The characteristic system of ODE is dx by dt equal to 1, dy by dt equal to 1, dz by dt equal to z square. Now, when we compute the base characteristics, x equal to x of ts equal to t plus s, because it is t plus constant, it has to be t plus s, y is just a t. Of course, z also can be integrated, we get 1 by s minus t. From the first two equations, we can solve for t and s in terms of x and y, because these are just linear equations, very easy to solve, and u equal to this 1 by x minus 2y. It is defined on the domain whenever x minus 2y is non-zero. So, you have to stick to one of them, because I do not want in my domain x equal to 2y happening. So, x is greater than 2y is one option, x is less than 2y is another option, but when x is greater than 2y I take x positive, or x is less than 2y I take x negative. Why is that? Because only this domain is in contact with the datum curve on which datum curve, a projection of the datum curve is intersecting only this part or this part. it is not intersecting uniformly x bigger than 2y. Okay. Now, both solutions are local with respect to datum curve solutions. So, local solution with respect to datum curve. Observe that base characteristics are the family of straight lines x equal to y plus s. See here y equal to t, right. So, y plus s, x minus y equal to s, that is a family of base characteristics and they fill entire plane. Still Cauchy problem does not have a global with respect to domain, forget about it, even with respect to datum curve it does not have a global solution. So, this is a manifestation of the nonlinearity in the right hand side, namely u square in the PDE. Let us look at example 6. Here we consider 2 Cauchy problems for the linear PDE minus yux plus xuy equal to 0. Posed, of course, I do not want coefficients x and y to vanish simultaneously, which happens at the origin. So, I remove the origin. On that domain I consider this equation. And the characteristic system of ODE we can directly write down, right. And base characteristics, because of this nature, dx by dt is minus y and dy by dt is x. So, if you compute one more derivative, d2x by dt square is minus dy by dt, that is equal to minus x. Therefore, d2x by dt square plus x equal to 0. Similarly, one can do with y. So, solutions of x and y are going to be solutions of y double dash plus y equal to 0, which are combination of cosine and sine, and the trajectories will be circles. So, base characteristics are the family of circles x square plus y square equal to c square. Since it is positive number, we write c square because we do not want to write root c in some other place. So, we write c square and always mention this that c is positive, so that we do not get confused later. Now, the equation for z implies that any solution to the PDE is constant along each of the base characteristics, because z is constant, right, dz by dt is 0 on solutions of this. Okay. So, that means on each circle the solution is constant. So, if you know at one point on the circle what is the value of the solution, then it is the same constant throughout that circle, on that circle. Okay. Cauchy data 1, we consider x equal to s, y equal to 0, z equal to s and s r minus 0. Okay. This is not that what we like, but it is okay. We continue with this, the computation. Gamma is not a curve, obviously it is 2 pieces, okay. But never mind, adjust for now. I guess one can create similar conditions, but then they look more complicated than this. This is very easy for computation. So, allow me this. So, I am going to compute with this. So, this is the initial conditions, and then solutions, as I said, cos t sin t the feature and z is s. Now, from the first 2 equations for positive s, I can eliminate or I can express, I think I should not use the word eliminate, I can express s and t in terms of x and y, I get this, and for s negative I get this expression for s. That is why negative for s negative, positive for s positive, t remains same. So, in both the cases the function s and t are not defined at points where x is 0, because when x is 0 there is a trouble, it is not defined. So, since z equal to s, the solution is given by uxy equal to sxy, therefore, uxy equal to this if x is negative, x positive. Now, it is defined on R2 minus x axis, and all points of gamma lie on the corresponding integral surface. So, this is global with respect to datum curve, not global with respect to domain, because it is not defined everywhere on R2 minus 0 0, no, it is defined on R2 minus x axis. Now, another function v defined on entire domain R2 minus 0 0 given by this formula, it is also PDE, but the problem is it is not a solution to the Cauchy problem. Why? For x in R minus 0, Vx0 is root x square, that is mod x on one hand, but Vx0 has to be x on the other hand, because that is the initial condition. So, both cannot happen. particularly for x negative, it is not possible. So, it is not a solution to the Cauchy problem throughout. Yes, if you restrict for x positive side, then yes. Okay. Cauchy data 2, here we look at x equal to s, y equal to 0, z equal to hs. So, it is like correction for the previous thing. Here mod x is an even function and here given data is not even function, that is why there is a problem. So, now I am going to change it to even function hs, where h is an even function. Still the same problem, but again adjust. Same procedure as above, we get uxy equal to a function h of root x square plus y square. This is defined whenever xy is different from origin and a smooth function. If h is differentiable C1 function, then this is being a composition of C1 functions, it will be a C1 function and it will be a solution. See now ux0 is h of mod x and that is equal to hx because it is an even function. Thus Cauchy problem has a solution defined on R2 minus origin. So, it has a global with respect to domain solution, therefore, global with respect to data as well. Solution is global with respect to both. So, let us summarize. Many Cauchy problems are solved using method of characteristics. Understood the local nature of solutions to first order PDEs. This we understood local nature can be in the sense two different senses. One is with respect to the datum curve, another is with respect to the domain. Of course, through two examples we have understood and reasons were different in each of these examples. And in a forthcoming lecture, an example of a Cauchy problem for Burgers equation will be studied. In that example, the local nature of a solution arises due to intersecting base characteristics, that we will see in a forthcoming lecture. So, with this we come to the end of quasi-linear equations and we will then start with the general nonlinear equation, once again Cauchy problem. We will be making regular comparisons to what we did in the Cauchy problem for quasi-linear equations. You may say that quasi-linear equation is a special case of general equation, why do 2 times, right? Why repetition, why do not you do the general thing first? No, because quasi-linear equation always when you do not understand something you would like to understand with a special case. Quasi-linear is one such special case where things are easily understood. Now we try to extend these ideas to the general case, that is what is the natural progression in solving problems in mathematics. Thank you.